Hey guys, today we are going to talk about inverse trig functions. So when we think about an inverse trig function, so we've been learning about inverse functions with learning about our log functions and exponentials. So a regular trig function that we've worked with before would be something like y equals sine of x. We learned that an inverse function switches the input and the output, so that'd be like x equals the sine of y. Then we need a way to get y alone again, and we can't like divide because it's not sine times y, it's the sine of y. Sine is a function itself. So the way we undo this is with what's called the inverse trig function, which we have two different ways to write. We can write it as the inverse sine with that little inverse symbol as meaning -1. Now, again, that is not an exponent of -1, because if it was, an exponent of -1 flips things to the bottom, and we know that sine on the bottom of a fraction is a cosecant. This is not a cosecant. It's a completely different kind of function. So that notation is not my favorite notation for it, but it is a notation for the inverse sine. The other notation that I like better is that we write arc in front of it, the arc sine. And that I like that better because then it doesn't have that confusion of whether it's an exponent or the inverse. So the first kind of problem you're going to have in your assignment is just about what this inverse trig function means. So when you have an inverse trig function, this is not calculus, this is algebra. Maybe you did it in, well, I think at our school we do it in both geometry and algebra too, and then you should have also done it in pre-calc, just evaluating the inverse trig function. So what this is asking is what angle has a cosine of 1/2. So the answer to an inverse function is it's looking for an angle. It's looking for the angle that has this as its answer. So cosine is, as we think about SOHCAHTOA, adjacent over hypotenuse. So we're looking for what angle is living in a triangle that has a hypotenuse of 2 and that is next to or adjacent to a 1. That would be a 60 degree. So the answer to this question is 60 degrees, except in calculus, we work in radians. So we're going to say that that's pi over 3. Pi is 180 degrees in radians, so 180 over 3 is 60. If you have a unit circle handy, then these are not a big deal. It's just you're looking, it's kind of like Jeopardy. I think of inverse trig like Jeopardy. You're looking back for what was the question that gave this as an answer. What was the angle that gave this fraction as the output? So that's the first kind of problem that you're gonna see is this this just evaluating an inverse trig function. So that's not what I wanted to do. Okay. So next what we want to do is we're actually going to look at some graphs here of these inverse functions. So this is the sine graph, y equals sine of x. So we've learned that switching out the x and the y creates the inverse. So if I switch out the x and the y, I get the inverse. So that would be this. But there's a problem with this green graph in that it is not a function. It really fails the vertical line test over and over and over. So what we do then is when we actually work with our inverse functions, which again you can define with the word arc or with that little -1, it is going to limit down the domain of the original function, which will then create an inverse function. So it's taking only a piece of this sine graph and saying, let's work with just that one piece. And then when we inverse that, we will still have a function. So that's what this is talking about here. So if we worked with the whole of the sine function, it would keep on going and that would cause a problem. So what we do is we limit it down so that we have a limited domain and range, but then we're working with a function instead of not a function, I guess. So here's what our graphs look like for our 6 arc trig function. So we have our arc sine here, arc cosine, arc tangent is just going to be one of the lines. Remember, a regular tangent function has the repetition of those lines in vertical asymptote sections. So when we do the inverse, that's going to switch it to horizontal asymptote sections, and we're just going to work with one of those sections. And then we have our 3 other functions down here as their inverses. So use these as reference as well when you're thinking about the graphs. And then your second kind of problem that you're going to be asked to do is going to be, so I'm going to switch back to Desmos to show you. The second kind of problem that you're going to ask to do in your homework is actually a calculus problem then. And so we're going to look at limits. So we're going to do something like a limit as x goes to -1 plus, remember that means from the right, of the arc or inverse cosine of x. So this is asking, as x goes to -1, what are we getting for the inverse cosine? Okay, again, thinking about this idea of the answer to a inverse trig function as being an angle, this is really kind of asking what angle are we close to when we have a cosine value of -1. Okay, that -1 not because the inverse -1, but because that's what x is approaching here. So as we get close to -1, what angle is creating that? You can do that on a unit circle, or you can do it with graphs. So we'll look at a graph here of this inverse cosine. Looks like this. And so as x goes to -1, the function is trying to be this right here. And it tells us that the function is trying to be pi. And again, thinking about a unit circle, the value of cosine of pi is -1. So that's that inverse relationship. Okay, so we have 2 kinds of questions that you're going to see so far. First, just evaluating the inverse trig functions, which is more of a pre-calc topic. We've done that before, but just remembering what these inverses are. And then our first calculus idea with them is these limits. And our limit in that example, remember, was coming from the right, because coming from the left can't happen. So, so it was a one-sided limit, necessarily, because there was nothing happening to the left there. So our next calculus topic then is going to be derivatives. And so let's see. These are all just still about functions and limiting domains. All right, so I'm going to show you where the derivative comes from. We're going to derive the derivative. That's kind of a weird thing to think about, but that means we're going to figure out what the derivative is and why it is for this inverse sine. And then the rest of them I'll just give you. We're not going to do them all, but I want you to see where these come from because they're kind of weird derivatives. So I want you to see why they are what they are. So if our inverse function, so let's say we started with, y equals sine of x, and then we did the inverse, we switched them. Well, again, notationally, we could say that this is the inverse sine of x, and so then now I want to find dy dx, but you don't know what the derivative of the inverse sine is, so we can't just do it. So we're going to use this other one, this x equals the sine of y, and we're going to take our derivative implicitly. So remember that implicit derivative is where y is within the function, and then we're just going to work with a dy dx like a chain rule. So the derivative of x is 1. The derivative of sine is cosine, and because there's a y, we're going to tag on a dy dx here. So then dy dx is going to be 1 over a cosine of y. Well, that's great, but it'd be nice if it had x's in it instead of y's. So what I'm going to do is draw up a picture of this relationship. So if I have an angle, that's y, because that y is inside of a sine, it should be an angle, and the sine of that y angle is x. Well, sine is opposite over hypotenuse, so that means opposite would be x and hypotenuse would be 1. X over 1 is x. So in this picture, the sine of y is x. So this is a picture of that original equation. Well, then we can use the Pythagorean theorem to find what this other side is, and that other side would be the square root of 1 minus x squared, just solving through the Pythagorean theorem there for what that other side would be. So if our derivative is 1 over the cosine of y, well, we can grab what is the cosine of y from that picture. The cosine of y, cosine is adjacent, which would be that square root side that we solve for, over hypotenuse, which is 1. So we don't need to write over 1. And so that is our dy dx. This is the derivative of the inverse sine, or arc sine, is this fraction of 1 over the square root of 1 minus x squared. Then obviously with our derivatives, if it was not just an inverse or arc sine of x, but it was of x squared or something else inside there, then we would need a chain rule applied to that. But because these derivatives are a little strange and that these square roots and stuff come out of them, I wanted you to see where this idea is coming from. But we're not going to go through the process of all of them. Some of them are better than others in terms of simplicity. So here are all of your formulas. If you want to pause it and write them down, or I'll talk about them here for a minute, but if you want to pause them and write them down or screenshot it or however it is that you are keeping reference to important formulas, these are things that I would not suggest memorizing. When we did this as an AP class, they technically had to be memorized, but I even told the students, like, it's still probably not totally worth it, because on the AP test there might be 1 or 2 questions that need these, and I mean, just look at them, they're pretty terrible. So one nice thing to notice about them is the cofunction derivative is the same but with a negative. So we have our sine derivative as formula number 1 there. Number 2, that arc cosine, it's exactly the same except it has a negative in front of it. Then tangent, the arc tangent one is the best one. I always hope when I'm working with arc functions that it's the tangent one, because there's no square roots involved in that one. And then formula 4, the cotangent, the arc cotangent, it just has a negative in with it for the cofunction. And then when you get a secant or a cosecant, hold your breath, because those are pretty gross there with that absolute value as well. But a lot of times in a problem, they will limit down the domain, and so that absolute value ends up being something that we can ignore. So go ahead and pause it if you need to keep writing those down. Otherwise, I'm going to go on to an example of finding a derivative. Okay, so we are going to find dy dx if y is equal to arc cosecant of 3x squared plus 1. And we're going to define x as being bigger than 0. Actually, that's not even really necessary on this. Okay, so I said hold your breath when we get those arcsecants or cosecants because they're the messiest one, and then that's why I decided to do this as an example, because if we can do the messiest one, then the other ones shouldn't be a problem. So to find dy dx, we're going to apply that arc cosecant derivative formula. It's a co-function, so it's going to have a negative in front of it. And then it's 1 over, and then the formula says the absolute value of u, or whatever's inside of that. So we're going to have absolute value of 3x squared plus 1. And then square root of u, whatever that inside function is, squared minus 1. And then because it's not just an x, it's an inside function, then we need chain rule times the derivative of the inside, which would be 6x. You don't have to do a lot of cleaning on these, actually. I tested it out with your homework program. How much cleaning did they want on this? So I typed it in, or something like this, as a negative 6x there. And then we can drop out the absolute values on it because squaring is going to give a positive, and then timesing 3 and adding 1, we only have positives in there. So I just changed it to a parentheses. I mean, I guess that doesn't make it that much cleaner, but it is a little bit. And then what I was really wondering is, would they want you to actually distribute out that square binomial and subtract the 1 and anything, and they didn't require it. So typing in something just like this would be fine. Just be careful with parentheses and stuff. Double check your notations before you try to submit the answer. But that's what we would do for a derivative. So again, don't bother in any way trying to memorize those formulas, really. It's just not worth it. But have them as easy reference, and then make sure that you pay attention to your chain rules. So we talked about how to evaluate inverse trig functions. We talked about calculus with limits, finding a limit, and we can do that graphically, or again thinking about using the unit circle backwards, just like evaluating. Now we've talked about derivatives, so the other calculus thing that we need to talk about for inverse trig functions is integrals. So for integrals, we have these 3 formulas here, which really, when we think about integrals, right, it's just a backwards derivative. So these formulas are really just kind of backwards this, but they do help to use these a little bit because they take that kind of chain rule into account a little bit with that a value there. So it does only give us our formulas here for our 3 primary functions, not the co-functions, but that's fine. So we're just going to work with these ones. So if you need to pause it to write these down or screenshot it or whatever, go ahead and do that. And then we're going to do an example with one of these. So I'm going to have the integral of dx over square root of 25 minus x squared. So what you'd want to do is look at those 3 formulas and see which one does this look like. And the formula that this looks like to me says dx over a squared minus u squared. And then what it says that is the arc or inverse sine of u over a plus c. So what we have to do is just kind of line up our pieces here and say this is going to be our inverse sine of u is x, so that's nice there, and then a, if a squared is 25, a must be 5, and then plus c. And so if we took the derivative of that inverse sine of x over 5, we would have a chain rule in there to take that derivative of x over 5, and this is what it would work out to be, kind of thinking again of that relationship, that fundamental theorem between derivatives and integrals and how we can work back and forth between them. So that is all I have for you about inverse trig functions. So how to evaluate them, how to do limits, derivatives, and integrals. So those are the things that you will need to know to be able to do this next section. So again, this was section 6. So that wraps up our lesson for today. So you can keep on working through. Now you can do all of your chapter 7 homework up through section